We are going to see biostratigraphy, and for that we need some background information, and then we will get into the detail. Biostratigraphy involves fossils and not just the biological specimens. Organisms have got two parts, hard and soft portions. Usually the soft part is destroyed, decomposed and is not preserved as fossil, and the hard part can get preserved. Flesh is the soft part and bone is the hard part. Now this hard part can be used to identify the fossil record. There are certain morphologies developed in the hard parts, and from that morphology we can decipher the fossil. Now these fossils can be used in the correlation. So now the use of fossils in biostratigraphy is not a straightforward process. Let's look at the biocenosis. What is that? They are the in situ variety of organisms that lived and then they stayed, and there itself they became fossilified. So the biocenosis will truly represent the paleo environment conditions or even the age of the rock. Whereas there is another variety of fossil, what can be called as the death assemblage or the thanatocenosis, where the organisms lived elsewhere, but after their death their hard parts were transported and then they got deposited elsewhere, and these fossils are known as the reworked fossils. So from the reworked fossils it is not possible to decipher the environment in which they were staying and the age of the rock. So a very important part in biostratigraphy is to distinguish the biocenosis and the reworked fossils. Any reworked fossils are to be excluded from the biostratigraphic studies. A strata which is devoid of fossil is called barren, and we will come across a word barren measures in Gondwana stratigraphy in India. A specific formation is named as the barren measures. How to identify the reworked fossils? The reworked fossil, suppose I take a garden snail and this of this geometry, now it gets transported to a long distance. This apical part, sharp conical region will get rounded. So all these reworked fossils get more rounded. Looking at the various examples of the fossils, you can then understand that these are untransported actual form and more rounded forms are the transported ones. The more rounded forms are to be avoided, and any broken piece is to be avoided. More rounded and broken piece means naturally it got transported, in the process of transportation it got broken into pieces, and those are to be avoided. Pick up the entire fossil, unbroken one, and use in biostratigraphy. In the geological history, the oldest age is the Paleozoic. This was followed by Mesozoic and then Cenozoic. What the Paleozoic means is ancient life. Paleo means past. Mesozoic means the middle life. Life has developed to a moderate extent and the vertebrates are well developed. Cenozoic is a recent life. Human evolution happened in the upper Cenozoic time. Mesozoic is the time when we had the dinosaurs prolifered in the Jurassic, and Paleozoic is the ancient life form. It started with soft-bodied organisms and they were hard to get preserved, and with time the hard shell started developing within the organism and the biostratigraphic correlation with those rocks became easier. So let's say the small shelly fossil of the Precambrian time, their identification is difficult and is also controversial. So establishing a stratigraphy entirely based on SSF is problematic. SSF has been used in India in the Vindhyan stratigraphy. Whether the so-called small shelly fossils are fossils at all, that also has been questioned. Now we will come to the biological definition of species, and this becomes important. What is a species? It is a group of interbreeding organisms that are reproductively isolated from each other. That means a group of interbreeding organisms which cannot breed with another such group. Such groups are called species, and it is the fundamental unit of defining or classifying the organisms on the earth. Is the fundamental unit to define and classify organisms. Now, the problem with paleontology is that one is only dealing with the hard parts of dead organisms, and from the dead organisms we do not really know whether they were able to interbreed. So, this part of the definition becomes problematic to follow by the paleontologists. That is what I am writing. Whether they were reproductively isolated cannot be checked for the fossils. So, the paleontologists mostly look at the shape or morphology of the fossils, and therefore geoscientists tend to define species as morphospecies. That means organisms of similar morphology will be taken as a species. But this morphospecies concept is naturally not always reliable. There can be two fossils similar looking, but in the past when the organisms were living, they were belonging to two different species. They were not able to interbreed. They had their own groups or their own species. Now, using morphospecies sometimes create biostratigraphic correlation. So, it is common that when a biostratigraphic column is created, at bottom there are certain organisms, and as one moves upward other organisms are found and are kept. Corrections of biostratigraphic column is very common. Many iterations are required to reach finally the more accurate biostratigraphic column. Once we have defined species in this way, this definition itself is not free from error. Take for example, a horse and a donkey can interbreed to produce a mule. Now this goes, horse and donkey belong to two different species. Now they are interbreeding and the species definition do not match. Then there are several birds which are genetically distinct, but they are similar looking. They have wings and their beaks and their legs are similar looking, but they can belong to different species. We also have the concept of subspecies. What is that? Organisms of same species, but they look different. For example, dogs. The street dogs in India or dogs in other countries, where you compare the mountainous region and the coastal region and the island region, the dogs look quite different, but they belong to the same species. So, these are some of the troubles of defining species, but geoscientists have to work on. When the soft part is available, the DNA study is done, and this is most accurate, but not always the DNA study is possible in the geological context. We are going to see the division of the living organisms on the earth, and this is known as the Linnean system. The species is defined in the way I told you, and it is not free from error. Similar species are grouped as genus. Similar genus form a family. Similar families are clubbed to define an order. Similar order can be clubbed to define a class. Similar class can be clubbed to define a phylum, and similar phylum will be called belonging to a kingdom. The first classification of kingdom is the animal kingdom and the plant kingdom. In this way, organisms on the earth has been classified. But again, this classification into two rigid parts, animal and plant, is not correct. For example, if you study the bacteria and virus, can you call all the time that they are plant or are they animals? Are they living beings or the semi-living beings? So, this becomes a problem. So, remember, even though we define species with a big problem, DNA is the key to define species, as I told you. Now, this sequence has to be remembered by you. The easy way to remember is SGFO, CPK and an arrow. Remember, SGFO, CPK and an arrow. Species, genus, family, order, class, phylum and kingdom. Kingdom is the highest unit in the Linnean system. Species is the lowest one. Species is defined first, and then similar species are grouped, similar genus are grouped, etc. Let us look at the human beings. The scientific name is Homo sapiens. We should underline in this way, and if I am typing, it should be in italics. here Homo is the genus and Sapiens is the species. Genus and species name are given side by side to define the scientific name. If you visit any botanical garden, you will find that along with all the trees, their scientific names are given. So the first one is the genus, the second word is the species. The genus starts with capital letter, and while writing the species, the starting letter has to be small. This is the convention. If I consider one of the ancestors of Homo sapiens, Homo erectus, here you can see Homo is the genus and erectus is the species. Besides this formal classification in the Linnean system, there are many subdivisions. Superfamily is a group of family and which we are not calling as order. Suborder is a subdivision of order and which may not be family. Subspecies, that means species can be divided into several subspecies. Now in biostratigraphy you will find the use of the word taxon and taxa. We have to understand. Taxon is a singular, taxa is the plural. Any one of them, if I want to refer either species or genus or family or order or class or phylum or kingdom, I can call it as a taxon. So this taxon can be S, G, F, O, C, P, K, any of these. And if I say taxon A is correlated with taxon B, that means what? Talking A as a species or genus or family or order or class or phylum or kingdom, and B can also be like that. When we do this biostratigraphic correlation, this sentence automatically means that we may be dealing with the species or the genus or the family or the order or the class or the phylum or the kingdom as per requirement. We need to understand the concept of temporal mixing. What does it mean? Here the word temporal is indicating time. Fossils can predate the stratum. What does this mean? Suppose this is a sedimentary deposit, capital S, and here within this shaded region some fossils are present, F. Now reworking happens, this sediment mixes up. This sediment was loose, so it was due to some high flow condition, high flow regime, this moves up and then start depositing. So what will happen? F can go inside the sediment. So in this way this fossil's age is younger than the sediment, but now it has been mixed up. In this way time wise mixing has happened, that is the meaning of the word temporal mixing. Such things have been found in the storm beds and where the fossils of 1000-year time gap has been mixed up. Here we were dealing with just one fossil F. Imagine there is F1 fossil and here there was F2 fossil. Now once the mixing has happened, F1 is here, F2 is here and F2 is here. So this is a case of mixing of fossils. So in this way temporal mixing takes place and a paleontologist, a biostratigrapher has to be alert in deciphering the biozone by avoiding this temporal mixing case. The other way of temporal mixing is bioturbation. Let us try to understand. Say this is a sediment column S and here some burrowing organism is making a burrow. This organism O came when the time was small t1 and as it has burrowed, it has reached a point which is equivalent to time t2. The sediment age can be time t2, but the trace fossil, the track is of age t1. So I can write at this point what is happening. Sediment age is t2 whereas burrowing organism is of age t1. So clearly at this point a temporal mixing has happened. We will now look at three kinds of snapshots. In fact, two are reported, another is only predicted. Syn depositional snapshot. What does it mean? Syn means simultaneous or coeval. Depositional, we understand sediments were depositing, and at that time the organisms were killed by some catastrophic event and then they got deposited. This is the meaning of syn depositional snapshot. Now, follow the definition: remains of organisms that were killed during a single event. So, if they get settled without getting caught up in any turbulence, then the syn depositional snapshot can be good in correlation. Next, we come to the pre-depositional snapshot. Now, this has not been documented and only has been predicted. What is pre-depositional snapshot? Organisms have died before the sediment deposition has taken place. The third variety is a post-depositional snapshot. What does it mean? That after the sediments got deposited, later post-depositional, the fossil evidences are coming into picture. An example is the colonization. There are many organisms which are delicate and which cannot sustain waves. So, if they develop a colony, they can sustain, and by staying in a colony, they protect themselves from the wave action. Now, this colonization happens much after the sedimentation took place. So, it is a post-depositional snapshot. Colonization is the example. I have referred earlier the burrowing organisms, but also remember in the context of this previous page when I was referring here that there can be burrowing which are partial, that the organism tried and failed. The paleontologists have worked out such examples where failed evidences are also there. The concept of mass extinction has to be understood very briefly when we study the biostratigraphy. There are 5 major mass extinction that have been documented on the earth. This has been global event, end of Ordovician, when it was a short lived ice age when many organisms got extinct from the earth, and after extinction happens, it has been observed that the same species does not come back, it never comes back. For example, we say crudely that the dinosaurs got extinct and the dinosaurs have not come back on the earth. Late Devonian is oceanic crisis and it led to many of the marine organisms to die. This oceanic crisis, one example can be oceanic acidification. Now, the other one is the end of Permian, and it was a most severe mass extinction in terms of the number of species lost and the ecological impact that has happened, and the reason can be giant eruption and climatic crisis. Massive eruption of the volcanic lava that changes the chemistry of the air and eventually soil and eventually the plants and eventually the animals through the food chain. The volcanic eruption also throws the ash particles high up in the atmosphere, and for many years the sunlight cannot penetrate to the full extent and the ecology gets severely disturbed. The end of Triassic is also a time of giant eruption and the climatic crisis. Then the end of Cretaceous, where the dinosaurs got extinct, large marine reptiles and ammonites also got extinct. So, these are the 5 major mass extinction. The 6th one is only predicted, Anthropocene and human induced mass extinction. Due to the advent of this civilization, many species have got extinct in last 300 or 400 years, and there is a chance that more species will go extinct. Let us look at the biostratigraphic unit. What is it? It is a body of rock. The physical entity of the biostratigraphic unit is that it is a body of rock, it is a volume of rock, and it is defined by its fossil content. Now, there are different kinds of biostratigraphic units. Let us have a look at them. The fundamental unit here is called biozone, and it is defined by the index fossil or the zone fossil. They are the same thing, index fossil or the zone fossil. With the help of them, we define biozone, which is the fundamental unit of biostratigraphy. And what is that? It is a volume of rock or body of a rock which is characterized by its fossil content. Now, we should choose the index fossils or the zone fossils in a way that they are independent of the lithology. Not always it is possible, and we will see further. Now, these zone fossils defining biozone can be found within the type section or the stratotype. This type section word also came in lithostratigraphy and the things have been explained there. Here in biostratigraphy also we use the word type section or stratotype, and it is defined by the taxon if it is a single organism, or taxa, that means more than one taxon. Now, what should be the ideal zone fossil or the ideal index fossil? It should have lived worldwide in all depositional environments, and if that is the case, that means index fossils found in one place of the world can be correlated with a basin which is hundreds of kilometers away from the observation. They should be abundant. If they were very few in number, there is a chance that they were not documented as fossils. Maybe they are fossilized, but the geologists do not know. So, if they are abundant, it becomes easy for geoscientists or the paleontologists to find out. And these ideal zone fossils should have easily preserved hard parts. Now, these hard parts were not there for the organisms which were too primitive. With time, in the beginning of Paleozoic, the organisms had got softer parts, and then there are much debate whether those are fossils or not. But when they have got hard parts, what can be the hard part? For example, bone, or if we are dealing with plant, it can be stem and also teeth of vertebrates. These are easily preserved. What is not easily preserved? The soft parts such as flesh. Note that there are rare examples where even flesh has been preserved. Fourth, the ideal zone fossil should be a part of evolutionary lineage and frequently altered to another species. What does this mean? Say this is time T1, this is time T2, this is time T3. For the ideal zone fossils, you might be able to tell that this is species 1 and here speciation happens, a new species goes from time T2 to T3. So, this point is marking. We expect that each species will also be possible to identify as a morphospecies. So, the morphology will be different. So, S1, S2 etc. can be identified. Now, imagine there is a fossil which has we find over a profound geological time T1 to T3 and it is species S, or let us say taxon T. No changes have happened over a very large geological time. Then we cannot call it an ideal zone fossil. The concept is we should find a shorter time range and with easily preserved hard part, abundant in number and found in many basins worldwide, so that this can be time wise correlated with another succession in another basin. And note that the correlation between marine and non-marine strata is a problem in stratigraphy. Why? Because the marine organisms and the non-marine organisms are usually distinct. There are very few organisms which stay both in marine and non-marine environment. An example which comes readily in mind is tortoise, or we can call turtle. Now, I am giving you a job. The students who are watching, check whether tortoise fossil is good for biostratigraphic correlation between marine and non-marine strata, to what extent it is possible, and do a self study. Is it a good biostratigraphic tool in correlation? If it is good, why, and if it is not good, why so? And can you name a few fossils which when were living were found in both in marine and non-marine environment, and using them such a correlation between marine and non-marine strata was possible. Now, in the marine environment, we can divide organisms into two types, planktonic and nectonic. Planktonic are those which are free floating, that means they cannot swim. Wherever is a flow, it is carried in that direction. The other is a nectonic, which is free swimming. So, they have some ability to flow against the current. Now, these two have got good use in biostratigraphy. We have a third variety of marine organisms called benthonic or benthic. It is not much useful. Why? Because it lies on the sea floor and it has a restricted movement. They are not widespread. Now, we have two varieties of benthic organism, sessile, which means it is immobile, it cannot move at all, and the other variety is called vagrant, which is movable. Be it immobile or little bit mobile, overall we can say the benthic sea organisms are not usually good in correlation, and there are examples where the benthic organisms have also been used in correlation. Now, interestingly, the benthic organisms' behavior with time may change. There are a few benthic organisms which in the larval stage, in the beginning stage, are free swimming, and in the later phase they become attached at some place on the ground and they have got very little movement. So, in such cases where the larval stage free swimming is possible, these may act as the zone fossils. In the context of biostratigraphy, we should know the definition of microfossil. First of all, why we call this word micro? Micro means that they are seen under microscope. That means in naked eye or even with a hand lens you cannot identify them. They are usually abundant in number. They are usually very much useful in biostratigraphic correlation. Microfossils are far more used than the macrofossils in biostratigraphic correlation. Microfossils usually preserved intact. They are not further broken since they are already very small in size. Whereas, think of a large bone of a vertebrate organism. If it is transported by water, there is a good chance that it will get broken. If it gets broken, then its identification becomes very difficult. Identification of microfossil under microscope is easy. The most widely used are the foraminifera or the forum. It has been so extensively used in biostratigraphy and in hydrocarbon industry. It has emerged as a separate set of knowledge and is known as foraminiferology. Logy means knowledge, just like geology where logy means the knowledge. Foraminiferology is the knowledge of the foraminifera. So, there are foraminifera experts who are very specialized in using them in biostratigraphic correlation and also in other studies.